Good day, everybody. Welcome to my presentation, which is entitled Continuous Sensing on Intermittent Power. Energy harvesting batteryless sensors collect power from perpetual energy sources, such as sunlight and RF transmissions. Therefore, they have the potential to operate indefinitely. However, harvested energy is weak and volatile. Therefore, these devices operate intermittently. They start by harvesting energy in a small capacitor. Once the harvested energy reaches the turn-on threshold, operations are triggered, which causes the buffered energy to be quickly depleted and the device to power down. This in turn allows the harvester to refill the buffer, and the cycle of charging-discharging continues. This intermittent style of operation has introduced many challenges. A number of these challenges has been tackled. For example, intermittent computing, which has to do with preserving the forward progress of a program despite frequent power failures. And the data freshness challenge, which focuses on the validity of the data after a power interrupt from a timing perspective. However, despite these challenges, intermittently powered sensors still suffer from a fundamental shortcoming, and that is the intermittency itself. To see why, let's consider the following scenario. Imagine that we want to develop a smart wallpaper using energy harvesting batteryless nodes. If a sensor is available only 25% of the time, then a person needs to repeat his command on average 4 times. Clearly, such a technology will not be able to drive future applications. Therefore, this paper focuses on the challenge of enabling intermittently powered sensors to sense continuously. One approach to tackle this challenge is to use many intermittently powered nodes instead of one. But the question becomes, how many should we use and how can we be efficient? We have tackled this challenge on 2 stages. First, we focused on the availability of the system without considering sensing. Simply, we wanted the system to be on for 90% or 100% of the time instead of being available only 25% of the time, for example. When we analyzed the system, we noticed that there are persistent differences between the length of the charge-discharge cycles or the power cycles of the node. This is significant because it forces the uptime of a node to vary after each power cycle relative to other nodes' power cycle. And this observation enabled us to model the collective availability of the system or the availability of the Coalesced intermittent sensor. As you can see here, given a certain number of nodes and a certain duty cycle, we can compute using this model the collective availability of the system. We have validated our model using real hardware and under different ambient energy conditions, showing its accuracy. At this stage, we have achieved the goal of controlling the availability of the system. But sensing is evil. It can hamper the achieved availability. To see how, let's consider the following scenario. Here we see the power traces of 2 nodes. At time t0, the node with the red trace switched to low power mode waiting for an event. At time t0 plus 30, the node with the green trace also switched to low power mode. At time t0 plus 50, both nodes reacted to an external event. However, the node with the red line could not completely capture the event because it spent significant amount of energy prior to the event. It died while capturing the event, while the node with the green graph captured the event successfully and then powered down for recharging. What we see after the event is the power cycles of the node become more synchronized compared to their state prior to the event. The reason for that is the node with the red line started its power cycle before the node with the green line. However, its power cycle became longer because it spent less time in the active state processing the event. And therefore, the power cycles after the event became more synchronized. And now the question, how can we eliminate this unwanted synchronization? One possible way to eliminate this unwanted synchronization is by using communication for coordination. However, we did not investigate this path because of the expected overhead. Instead, we proposed a probabilistic approach. Its basic idea is if a node can make an educated guess about the number of active nodes at a certain moment, then it can respond to external event with a certain probability such that the power cycles of the nodes will not be synchronized. For a node to know the number of active nodes, it needs to know the total number of nodes in its Coalesced intermittent sensor and to measure its own duty cycle. For the details on how a node measures its own off time and the associated math, I refer the interested listener to the paper. At this stage, we have all the ingredients needed to design a system that can sense continuously despite the intermittent power supply. To experiment with our probabilistic approach, we prototyped a Coalesced intermittent sensor of 8 batteryless solar-powered nodes. The first experiment was to see the effect of increasing ambient energy levels and the inter-arrival time between the events on the total number of detected events and the uniquely detected ones. We see there is a positive relationship between the light intensity and the number of detected events. Also, when we increase the inter-arrival time, indicated with the red numbers below the bar, the number of detected events increased also. Furthermore, in favorable energy conditions, we see there are a lot of duplicated events. When we activated the probabilistic response, the number of duplicated events reduced to the half, while only 7% of the uniquely detected events were lost. Next, we experimented with the system response to bursty events. Each burst consists of 4 events. When the probabilistic response is deactivated, we see that most of the nodes respond to the first event in the burst and miss the subsequent ones. This highlights the problem of synchronizing the power cycles of the node on some events, which causes the system to miss others. On the other hand, when the probabilistic response is activated, we see that the system is able to capture the entire events with high probability. And with that, we are now able to develop the smart wallpaper that can capture commands of a few words despite the intermittent power supply. Thank you very much.